Welcome to this explainer. Today we're diving straight into what I consider the ultimate engineering challenge, systematically selecting the exact right plastics and their composites for a specific application. With thousands of options out there, making the right call is literally the difference between your product succeeding brilliantly or failing catastrophically. So let's jump right in.
Here is our roadmap for today. We're going to use a funnel approach. We'll start with the material selection challenge, move into defining operational requirements, map out a plastics decision pathway, unlock the power of composites, and finally, wrap up with thermoplastic elastomers.
All right, Section 1, the material selection challenge. Now, picking a material is way more than just grabbing a familiar name from a catalog, right? Because at the end of the day, base chemistry dictates real-world limits. Basically, we've got two main camps here. First, thermoplastics, which rely on crystallinity and an endothermic melting process. Then you have thermosets, which are completely different. They rely on cross-linking and an exothermic curing process. Because of this fundamental structural difference, thermosets are generally going to give you higher continuous use temperatures, while thermoplastics give us that critical melt processability.
But honestly, here is one of the most fascinating secrets in the industry. Simply being smart about your molding process might actually be more effective and way cheaper than hunting down some highly specialized polymer. It's true. Tweaking processing conditions, things like melt temperature and injection pressure, can actually alter a polymer's properties more drastically than just throwing out the material and starting over. You don't always need a brand new expensive plastic. Sometimes you just need smarter processing.
Moving on to Section 2, defining operational requirements. Okay. Before we even glance at a specific material, we have to define exactly what the part needs to do. And honestly, this is usually the hardest part of the whole process. Imagine you're designing a housing for computer equipment. You can't just guess. You have to systematically check off these 5 criteria. You start with strict regulations, like flammability standards. Then you map out mechanical properties, environmental operating conditions, electrical requirements, and finally, how the part will physically be fabricated. You absolutely have to know your destination before you start the journey.
Section 3, the plastics decision pathway.
So, with our requirements locked in, we need a logical decision tree to navigate this massive universe of plastics without getting completely lost. And we start right here at our baseline, polypropylene, or PP. Why PP? Well, it's our default anchor point because it's incredibly inexpensive and highly versatile. It's got low density, reasonable toughness, and really good hot water resistance. It basically gives us a fantastic, practical baseline to compare absolutely everything else against.
From that baseline, it's just about following the pathway based on your operational requirements. If PP is too hard for your application, you veer one way toward polyethylene or EVA. If it's too soft, you move over to polystyrene or ABS. Say you need transparency, then you're going to look at PMMA or polycarbonate. And if you need extreme load-bearing capabilities, you branch out to engineering plastics like nylons. See, it's a highly logical flow. But wait, what if the base polymer just isn't strong enough or simply can't handle extreme temperatures? This question brings us to a really critical turning point in our explainer. It's that exact moment when standard commodity plastics fail our rigorous operational requirements, and we actually have to step up and engineer a better solution.
Check this out. By making incredibly slight chemical modifications to high-temperature thermoplastics, we can engineer that better solution. For instance, look at what happens when you just swap the R group structure from an ether group to a sulfone group. Your glass transition temperature rockets from 180 degrees all the way up to 245 degrees Celsius, and you get a major shift in tensile modulus too. It's all about tweaking the chemistry.
Which brings us to Section 4, the power of composites. Sometimes, even those high-temperature thermoplastics aren't quite enough for a specific application. That's when we blend polymers with fillers to engineer completely new properties. By tossing in macroscopic fillers with high aspect ratios, we can massively boost stiffness and heat distortion temperatures. Glass fiber is going to give you the strongest reinforcing effect, but you definitely have to use coupling agents to manage the polymer-to-particle interface. Mica flakes? They're great for increasing modulus while keeping your impact resistance intact. The catch, though, is that while these macroscopic fillers bump up stiffness, they can unfortunately make the material harder to process.
So it's all about finding a balance. And the real cutting edge of this field? That would be nanocomposites. This involves using tiny amounts. We're talking less than 5 weight% of nanoparticles. By shrinking the filler down to the nanometer scale, you completely shift the performance dynamics because you maximize that crucial interfacial area. The result? Enhanced modulus, greater strength,
and better gas impermeability, literally without sacrificing processability. It's a total game changer.
Finally, Section 5. Thermoplastic elastomers explained.
Now we're looking at a revolutionary class of materials that seriously blur the lines between standard melt-processable plastics and traditional thermoset rubbers. Unlike the irreversible chemical vulcanization you get with conventional rubber, thermoplastic elastomers, or TPEs, utilize this really elegant reversible physical cross-linking under heat. This gives you impressive mechanical properties that rival traditional rubbers, but with the manufacturing ease of a standard thermoplastic.
So the magic trick here is block copolymerization. TPEs utilize both hard and soft segments. The soft segments give you the elasticity and dictate your minimum surface temperature. Meanwhile, the hard segments melt so you can easily process the material, but then they form physical crosslinks as they cool. They act as structural anchors, essentially trapping those rubbery soft segments in an elastic network. 299 million. Back in 2013, the world was already churning out 299 million tons of plastics per year. Think about that for a second. This massive number highlights exactly why a systematic selection pathway is so vital. We are practically swimming in options, which means engineering the perfect fit for your specific application is paramount.
So as we continue to push the boundaries of nanocomposites and highly engineered TPEs, will traditional macroscopic fillers and irreversible thermosets just become relics of the past? Or, at the end of the day, will raw material costs always dictate our engineering choices? I'll leave you with that provocative thought to ponder as you approach your next design challenge. I really encourage you to keep exploring this fascinating universe of material science. Thanks for joining me in this explainer.